Okay, good morning, everyone. Welcome to day two. We had a jam-packed first day, as we will today as well. So I'm really excited for all the science that will get done. Um, so before we begin, a short announcement that tonight's reception will be inside, although the roof access, although the roof access is still available, especially at lunchtime if you don't feel comfortable eating inside. Um, and Rachel will provide some more logistical updates right after this morning's plenary talk. So it's my absolute pleasure to welcome Leanne Guy, who's going to tell us more about the Rubin Science platform and what we can expect in the upcoming years. Thanks so much.
Okay, thank you, Ashley. For those of you who don't know me, I'm Leanne Guy. I'm the data management scientist at LSST, and I'm also the lead for the Department of System Performance Department once we get into operations. So I'm going to talk to you today about the Rubin Science Platform, about its design, about what you can expect from it, and how you can start to get involved early. Oops. Okay, so the science platform. The original concept for the science platform came several years ago. In fact, Mario Juric, who's in the room today, was one of the leaders of the vision for the science platform, which is we define as a set of integrated web applications and services deployed at data access centers through which the scientific community will visualize, subset, and perform next to the data analysis of the Rubin data products. And this science platform was designed with several concepts in mind, very specific to LSST. So to enable petascale analysis of the LSST data, to enable exploratory analysis through browsing and visualization, so an interactive component, to enable bringing your analysis to the data as opposed to the traditional download the data set to your computer, load it in memory, and do an analysis. It's also been designed to support user-generated product creation. So it's not just that it's serving the LSST data products, it's also allowing you, the community, to generate new data products based on your analyses, using the data products created by the project. It will integrate with existing archives via the IVOA protocols. We adopt a VO-first strategy for the development of the Rubin Science Platform. It provides collaborative working environments. So if you want to dynamically create a small group of people who are working on a paper, you can set up an environment. You will be able to set up an environment within the science platform to work collaboratively together to access the same code, to access the same derived data products. And behind the science platform, we provide back-end computation and analysis resources. So this is storage and CPU that will allow you to run your jobs. So these are some of the drivers for the Rubin Science Platform. The design of the science platform contains three aspects. The portal aspect, which will enable exploratory analysis and visualization. So you come in, you don't know what's there, you want to have a look, you just want to wander around. That's a very good way to start through the portal. Then the notebook access allows you to write Python notebooks, Jupyter notebooks in Python, and do in-depth next to the data analysis. So you can set off processing jobs and create your science data products. And then the API aspect enables remote access to other archives via virtual observatory interfaces. So if you want to, say, for example, connect to the Gaia archive, bring in some Gaia data for the objects you're looking at, you can do that. And I'll give you an example of how to do that in this talk. So let's take a little bit of a look at where we're at with these aspects. We're well beyond the design phase now. We do have a version of the early version of the RSP deployed, and it's being used. The examples I'm going to show you today are all real examples that are running at the interim data facility, which I'll talk a little bit more about in a minute. So this shows you the portal aspect, which is designed for discovery and interactive exploratory analysis. And here you see an example of a query that's being conducted it's a cone search through a region. You see the data plotted, color magnitude diagram on the right, and then you see all the data points. And so this allows you to just execute quick queries and have a look and explore the data a little bit. You can visualize images. You will be able to visualize LST images, and this was created using ADQL. So you use forms, subsetting, ADQL to generate, to get your data sets. And the portal aspect provides nice automated plotting of basic scientific graphics like this. So this is a great place to start if you just want to start exploring the data set and you don't know what's there. It requires very little programming knowledge. Here's an example of how you would do this. In fact, this is the exact query that I used to generate the previous image. You, let's see if I can, over here. So this shows you the portal interface. You can have an interactive display here where you can input a right ascension, a declination. You can put in a few other filters. So like I want a cone search of 1 degree radius. I can then pull up the catalog. Here I'm pulling up the desk DC2 object catalog, and I'm applying some filters on the G magnitude, the I magnitude, on the errors associated, and on some of the flags that allow you to filter for objects. And you just have to put these parameters in here. You execute the query, and you will get the display that I just showed you. You can also do this directly through ADQL by choosing enter ADQL, and you can actually write the query yourself. So if you know SQL, you know ADQL, you can just write the query yourself. You can also interactively search through the tables, and the schemas, and it will come up and help you to build these ADQL queries for you. So this is a great way to start if you've never used ADQL and you're not familiar with the data products. Once you get a little bit more familiar with the data products and you want to do some more in-depth analysis, you can move on to, you don't have to move on to, you can use these two in parallel, but the notebook aspect allows you to write Jupyter notebooks and execute them on the data sets hosted at the data facility. This here shows you, this is one of the tutorials, in fact, that we've developed for Data Preview 0.1. These are the tutorial notebooks. The link is down here. You can go to these and find all these notebooks. And this shows you an example of executing the same or a similar ADQL query that you write in a Jupyter notebook. You execute it. You can execute it through the same API, and it brings you up an image. And you can plot these images, and depending on the tools you use, you can interactively interact with these images that are returned through the ADQL query. You can annotate them with various information. You can hover. You can find details about them. So this allows you to do more in-depth analysis of the data and to start to build jobs that you might want to send off for large-scale batch processing. The environments on the Science platform come pre-installed with a variety of libraries. So we provide the LSST Science pipelines, so the exact versions of the pipelines used to generate the data products, as well as some very familiar tools, Anaconda, AstroPy, and many other Python packages that you will be familiar with. Users can also install additional tools in your environment. Again, you can use ADQL within the notebook aspect. And sitting behind this at the Data Access Center, we have computational resources that will allow you to run these notebooks. Here's an example of an interactive visualization using the notebook aspect. This was provided by Keith Bechtel. A query has been executed centered on a position in the sky. The data is returned. This is using the Dark Energy Survey's DR1 data set. You can find the link, the reference to the exact data set if you want to reproduce it here. It shows you an example of advanced visualization you can do with these notebooks. This uses the HoloViz tools, where you can link two plots, hover over one which is in the RAN deck plot, and then you can find the exact same points on a color magnitude diagram here. So this allows you to do interactive exploration in different spaces with notebooks. The HoloViz tools are very powerful. And so finally, the API aspect, this allows integration with external archives. The Rubin data centers will not host every survey data set ever known. So if you want to work with other data sets, you'll need to access them somehow. So as I mentioned, we have a VO first strategy where we use IVOA protocols wherever possible. So for catalog access, we use the TAP, which is Table Access Protocol. You can find details about it down here. Oh, what just, did not mean to hit that. Now I don't know how to get out of this.
Now we can all read the IPOA.
Great, wonderful. How boring. Technical help. How do I get out of this? I accidentally hit a link and I need to go back. Yeah. Yeah, it's not getting me out of it. There we go. Thank you. There we go. Yeah. Into full screen. There we go. Thank you very much. Yes, we all have technical difficulties from time to time. Um, okay, so this shows you an example here of using a tool called TopCat. Some of you may be familiar with. TopCat you can install on your computer, and you can use the TAP API to connect to connect to a data set hosted somewhere at an archive, and query the data and bring it back and create some plots locally on your computer. These same tools are integrated within the Science platform, and they're also used internally within the Science platform as well. So it's not just for access to external archives. The same tools are used internally to access the data sets at the US data facility, the LSST data sets. So as I've mentioned, there's also a variety of backend services, databases, images, files. These are also exposed through machine accessible web APIs. And just finally, these three aspects, they're not independent and completely separated, they are fully integrated. So you will eventually be able to execute a query in the portal aspect and access that result set in any of the other aspects. We don't have that running fully yet, but that is part of the vision. So here's an example I just mentioned before, using the portal aspect. Instead of selecting the LSST TAP service, which is hosted at the IDF, I've now gone to the Gaia archive. So the portal aspect already running at the interim data facility exposes a variety of TAP services, the URSA, Gaia, CADC, the master images. So I can select any one of these TAP services, and it will bring up in the schema browser the schema for that archive. So here I have the Gaia data release 2. You can see here Gaia data release 2 has been brought up with all the different tables. I then execute an ADQL query on the Gaia data. And here you can see in the portal display, I get an image of Gaia with all the points in this is like a cone search that I've executed, and all the data points. So if you're doing an analysis and you want to pull in some data from Gaia, you can do that. Fine, that's okay.
Other science platforms obviously want to enable cross-matching. Like their solution is just post every data set ever, and then allow you to cross-match locally. Here, this is obviously scales a lot better. You use TAP, but imagine if I wanted to cross-match all of Gaia to LSST.
So clearly, you're going to be limited by what the VO service can host, right? So this is not the way you would do a cross-matching of two giant great surveys. That would require co-hosting is obviously a better solution for that.
Okay.
Okay, something else that we will provide is called the image cutout service. People are going to want to retrieve images associated with the data they analyze, or just cutouts of images. You don't necessarily want the whole image, you just want a small part of the image. So the image cutout service will be implemented also using an IBOA standard, supporting both synchronous and asynchronous modes, and will allow you to execute a query where you can get, here's an example of a circular cutout, a polygon cutout, and a latitude, longitude based cutout. So you can specify the parameters and just get back the part of the query, the part of the image that you're interested in that's associated with your work. Okay, so that's what the Science platform provides. That's how you would interact with the data. As I mentioned earlier, the Science platform is also developed for user computing, for you to do your analysis. And some of the use cases that we've thought about in terms of user computing. And in fact, some of them we came across yesterday in the breakouts. People talked about these things like, for example, processing simulated images and comparing with the LSST data products. You might want to run exactly the same version of the Science pipelines on a simulated data set as we do on the real data. Reprocessing of images with synthetic sources injected to evaluate performance. Re-estimation of sky background is a common use case as well. Processing postage stamps from calibrated images. Training machine learning classifiers is, I think, one that's going to be very common as well. Computing periodograms on time series data from the source catalog. This is something we discussed yesterday. I think a few of the breakouts came across this and will probably be a very common use case. And as you've just mentioned, cross-matching with other astronomical catalogs. So in designing the computing services for users, these are a lot of the use cases that we've taken into account. We have a document here where you can read up on our use cases, but I think there's a lot of interesting use cases have been discussed already today at this meeting that might also help us to think about how we should design the user computing services. So user batch services, this is something we're working on at the moment. It's not available yet, these are the user-facing computational capabilities that will be available to you to execute these use cases. So if you want to do a cross-match, if you want to compute periodograms, we will support running in bulk over both catalog and image data. Oops. Sensitive. And provide a framework in which to do this. You might want to just run free-form jobs. You might want to rerun jobs. You might want to change some parameters and reprocess. These are sort of all the use cases we're thinking about in terms of batch processing and what we expect the users to want to do. There will be a resource allocation mechanism for users. So there isn't unlimited computing. There isn't unlimited storage. There will be quotas which can be modified per user, and that can be associated with predefined groups as well. So if you team up in a group, you're working on a particular analysis, there might be ad hoc collaborations or science collaborations could maybe request a different allocation. How much capacity is available for user computing is something that's been asked a lot. We have defined, and many of you have probably heard this already, an amount, the capacity for user computing is defined as at least 10% of the total LSST data processing capacity. This is for computing and storage, is to be set aside for level 3, or this is what's called user-generated production. Now, we know that this 10% will not be enough to satisfy the needs of the dark energy science collaboration. And we also assume that the desk will have resources provided elsewhere, typically NERSC, and we will work with NERSC to ensure that the resources for desk at NERSC can access the data sets. So when we think about this 10%, we think about this user computing capacity, we're focusing much more on the needs of the smaller needs of the communities outside of the desk who have dedicated resources, and to how we can provide meaningful access and resources to that community to do their science. I think I've already touched on this a little bit, but I'll just mention again that the RSP will support the creation and sharing of data sets for collaborative work. So dynamic ad hoc creation of user-defined groups. If you get a group of people together to work on a topic or a paper, you can dynamically create a group who can share data, access to data products, access to outputs. These are like virtual workspaces that you can create. These will be accessible across all the aspects of the science platform and also make use of the IVOA protocols. This is not yet in production, but it will be in the future. Some of the back-end services, I've mentioned this just a little bit already. All these user-facing services that I've just talked about are built on top of a number of back-end services. So for the databases, there will be the LSST prompt database and the data release databases. These will include all the data products, and they are stored in relational databases. So these will be available via ADQL. I think most of you are probably familiar with ADQL. You would query a relational database to get that data, as I showed you in some of the first examples. File services will be provided, so you'll have per user file space allocations. Users can upload code, store selected outputs, transform their outputs, subset the data. And then behind the scenes, there is computing services, so you can perform analyses via all 3 aspects, and you can serve the results on a shared computing cluster, share them with your colleagues, and access them via all 3 aspects of the science platform. So just some of the design principles I'll just go over here. The science platform is open source. You can go to GitHub and you can get the source code for this. It's been designed with reuse in mind. In fact, we have several instances of the science platform running at different places at the moment. It's also designed for ease of deployment, so it makes use of Docker and Kubernetes for container orchestration. One of the interesting points about this is that we can also create custom containers, which might include the science platform plus additional software. We do this already at the summit. So we have the software for the telescope and site team in the same container as the science platform code, so that they get direct access to the code through the science platform. And something to think about is that maybe we could do this with the Link software as well, create a custom container. Yep, I think I've covered the rest of that. Okay, does anyone have any questions on that? Because I'm going to move on to a slightly different topic here about the data previews. Are there any further questions on that? Yeah.
Sorry. Do you have a sense of scale in terms of what you're going to be able to support? For instance, we heard a lot about people wanting custom-sized postage stamps, which you clearly support. But do you think the sense is you could do that for a few hundred, a few thousand, a few million? What's the scale that you think
for
platform will work at?
You mean for the number of cutouts,
Yeah, so if you imagine if I had one point on the sky and I wanted to return all of the custom size cutout for all of the stack of images that have been taken up at that point, what's the scale that things would work well before you'd have to move it to something else?
So the cutout size we define as 30 by 30 pixels. As I think is the maximum. Will, do you? I'm not sure I can put any numbers on that, right?
I'm not sure we said it. The cut that you're thinking of the daily cutouts for alerts.
Yeah.
There's an image cutout service that's not limited. I mean, it will be limited, but it'll be more like 3 or something. It won't be tiny.
Yeah, sorry, that is the alert, the size of the postage stamp in the alert.
The question is how efficient that service is going to be, and that we don't know yet. And this is all of these things are going to be basically resource limited. We have a certain amount of processor power. If Andy comes and asks for 10 million cutouts and they take 2 weeks, maybe nobody else is going to get a cutout for 2 weeks, and they might be very happy.
I can imagine the email that I get.
And of course, it won't be so simple. It won't be that, oh, we're doing one cutout for one user. That can't happen. I'm sure we'll be able to support like tens, hundreds of users doing small jobs, and maybe we'll end up doing queues of, oh, long job. You want lots? Okay, you're on this queue. You want 2? You're on this queue, and so we'll figure out a way of making this, I think, okay for users. We haven't done it yet. We've just put out the first version of the image cutout service, so we can start playing with this with DP 0.2. So that's the good thing. We have a couple of years.
It's coming in DP.
I'm going to play with it already.
Okay, thank you.
I'll let you cue them up.
Can you say a little bit more about larger scale processing? So one of the advantages of having a data center, I think back in NCSA, was that it sat kind of next to a larger scale computing that was plugged into Exceed and other national resources. Now that it's at Slack, let's say if one wanted, to 10 million core hours on a resource, are there any provisions to get that either at Slack or at some of the other national centers with the idea that
computing for how much you'll get access to, how much is
like what's the recommended way to do large scale processing on LSST or to get cycles for them?
And we'll do that at Slack. Slack have some like equivalent spot computing. They have unused resources that we will have access to. We haven't set up the time allocation committee yet, but the idea is we'll have a body that you can apply to and say, I need this number of CPU hours, and we'll try to figure out, where we have that and when we can get, again, it'll be queued and resource limited. The other thing that we're going to try and do, well, what we're doing right now, we're on Google. We'd like to stay on Google to some extent. And so one possibility would be if you have money, you could go to Google and say, hey, I have 10K to spend on Google. I'm going to get all these CPUs. We give you access to the buckets, basically, so you can access the images on Google directly. And then you spend your money on Google for that. If it's the desk case, we're probably going to end up, pushing all the images to NERSC for desk. So then if you get NERSC hours, the images will be there. We just have to give you access. And if you get hours in Slack, the images will be there, and you can do that.
And then connections to Nsf Resources like Exceed or other.
So we haven't looked at those. So I mean, in the previous iteration, when we were NCSA, we were looking at Blue Waters, which would have become Exceed or something like that, or Frontera it's called now, and it's now in TAC. I'm kind of assuming NSF haven't asked us that yet, but I'm kind of assuming NSF are going to say we should put that data somewhere near Nsf Resources. But at this moment in time, they haven't requested that, and we haven't looked into it. But it's, if a lot of people are going to say, oh, but I'm going to get a bunch of hours on Frontera, it would be really good if we had the images from Ruben in TAC, for example, so I could access them with Frontera. I think we've basically said we'll do bulk transfers to large data centers for this type of activity. And again, we haven't firm plans for that because no one's coming, apart from Desk, where the plan is reasonably secure. They're going to be at NERSC, where we're at a DOE lab. We have really fast links to NERSC. We don't see any problem with making that happen one way or another. And the same is going to be true, I think, of any other large, like TAC would be the same. They're on internet too. We can get the data there. So I think once we have some people with real plans that they want to do this, we'll figure out how we'll support that. And the biggest problem is the authentication access. But if it's a big job like that and it's going to a secure lab, that's less of a problem. It's why we're not saying just anybody can ask for all the data.
Yeah. Okay. So I'll try to just go quickly through this. I'm now going to talk about the data previews. So in order to prepare both the community and the project to host and serve the data, once we get into operations, we've set up a set of what are called data previews, and this provides access to the data for the community to do early science. There are 3 planned data previews leading up to the start of operations. DP0, which is going to be based on the Desk simulated dataset, DC2. Some of you may be familiar with DP0.1, which is we are hosting the Desk simulated data products. DP0.2 is coming out in June, which will be the same data set, same images from DC2, but reprocessed with a more recent version of the science pipeline. DP1 will then be based on the commissioning data taken with the commissioning camera, and then DP2 will be based on the commissioning data taken with the LSST camera. So you will get access to all the data that we collect through commissioning via these data previews. For DP0.1, we had 300 what we call delegates who got access in June. We cannot yet just open it up to everyone. We also need to scale up our services and understand how to scale up correctly. So we opened it up to 300 delegates last year who've been actively working with the Desk data products. And we're going to open up DP0.2 very shortly. This gives you, I won't go through this in detail, but this is more for your reference. This gives you the data preview schedule and the contents. You can see here, these are all the data products from data release processing. These are the various data previews and the dates which we expect them to come out. Bear in mind that they are contingent upon project progress. And you can see here the list of data products and when you can expect to get them from through a data preview. We have 2 data facilities that I just want to mention to you. We have several data facilities, but 2 I think which are of interest to this community. The US data facility is the operations era data facility for processing all the LSST data. It is at SLAC. And we also have 2 facilities, one in France and one in the UK, which will help to process the data that comes from LSST. As these data facilities aren't yet fully commissioned, they're not yet ready for use. So in the interim, we've set up what's called the interim data facility, the IDF. This is a Google cloud-based data facility. We've partnered with Google to host the data preview program on Google Cloud. This is not a prototype. It's not a proof of concept. It is a full-scale production environment. It is being used to host Data Preview 0 at the moment, and we're preparing to set up Data Preview.2 for June. And this allows us to run our services as we develop our services, as we get ready to put them into production. This allows us to run our services at scale in a real production environment and to ensure a very high degree of readiness for survey operations and hosting the data when we get into commissioning and when we start to get into the beginning of the survey. And it also provides a platform for the community to start to access the data products, think about their analyses, and think about how they're going to work with the LSST data when it becomes available. This is the user interface to the science platform hosted at the IDF. We have 300 people already. We're scaling up to 600 users for DP0.2. And I would strongly encourage you to apply to become a delegate. There is this link here. If you go to this link, you can find the instructions for applying to get access to DP0.2. This will give you an account at the interim data facility, access via the Ruben Science platform, and access to the reprocessed Desk images, reprocessed with the latest version of the science pipelines. This is just for your reference, some links to tutorials and documentation. We're also putting a lot of effort into training the community, resources, documentation, tutorial notebooks. We also have a community forum set up. I think many of you are probably familiar with it. If you are using the Science platform, you can go to community.lsst.org. If you select support Rubin Science Platform, there's also a support for DP0.2, DP0 data preview 0, sorry, all of the data previews. This is where you should go to ask questions, find out information, share information. We're building up a community here so that everyone can help everyone, rather than have a help desk, which typically ends up with bottlenecks. This open forum will help everyone to share their experiences and for the community to help each other. And just finally, I was asked to highlight some aspects of research inclusion in the Science platform. Obviously, being a survey with LSST, that means that there are no proposals needed to get the data. So the RSP provides equitable access to all data products to the whole community. You don't have to go through these long, lengthy proposals to get access to data. The bringing the code to the data concept for the Science platform, this reduces barriers to entry. So all you need is your laptop and a good internet connection. Every single one of you here now could connect to the Science platform. You don't need to have access to a powerful computer center. You don't need to buy these resources. And so this makes the barrier for entry much lower for people. Our code base is open source. We have several instances running in the UK and France at the US data facility at SLAC. We also have an instance running at the Summit for our commissioning work, and we have an instance running at the cloud. So if you want to deploy an instance of the Science platform, you could go to GitHub, you could get the code and you could deploy it if you want. And in terms of access to the data previews, we're putting a lot of effort into making sure that we prioritize underrepresented and under-resourced communities to try to boost diversity and help people typically with fewer resources to get started to get involved with this program. Here I just have a link to some relevant documentation if you want to go and learn a bit more about some of the things I've spoken about today. And I will end with a video taken at the Summit by Eduardo Serrano just a few days ago to show you exactly what LSST looks like at the moment. This is a beautiful aerial view of the Summit. And it's very exciting to see these videos. It's very exciting to see it all come together. This is 3 days ago. Yeah. Not a render. It's only 1 minute, don't worry. Should have put some sound to it. Yeah, and that's it. So yeah. Happy to take more questions.
Rachel to see. So first, let me ask you just this question. There are many helpful links. Where will this slide deck be posted?
You tell me. I'll give it to you.
At least, but we can also post probably on the website. Thank you. Okay.
I will give you the presentation. You can post it wherever you want.
Thanks so much. We are over time. I'm looking at Rachel to see, but do we have any Zoom questions? The Zoom questions?
On Zoom. Okay,
answered. Great. Let's take one question from the audience in the room then, and otherwise you might get a lot of visitors at coffee time. Yeah.
So my question is, would RSP allow user-built Docker image to add on top the LSST Docker image currently or in the future? User-built Docker image.
A user-built Docker image on top of it.
So we will not allow just any user to build a Docker image and deploy it. That would cause all sorts of security risks. So we build for the Summit, and we assume there'll be a few large sort of groups like Link with professional developers where we would partner with them and accept a Link image, which would have stuff in it, and that the users who want additional things that we don't provide would go into that image. I'm assuming we would end up with maybe a handful of these. So at the moment, when you hit the RSP, you get a choice of builds. So you can have this week's, last week's, the current released version, the last released version. You can go back and find any released version, basically, of the stack. of pipeline software. And I'm assuming what we'd end up with is that plus, oh, here's the link version 1, 2, 3, 4, but not just your user code.
Yeah.
Now, as a developer, if you're at Slack, you could do something like that. We allow you to build, like for batch stuff, you can build a container and you can run it. That's in a different environment, and you have to be a Slack user. It'll be a lot more onerous than using the Sinus platform to get access. And it's a slightly different use case.
Okay, thank you.
Thanks, Lan. Okay. Okay, so okay, so the next thing we have happening is breakouts. And so I'm just going to spend a few minutes going over the breakout plan for today, including this morning and this afternoon, just to help us make the most of our time together. I should say that I plan to put a link to these slides into the Slack right after this session. So if you need to refer to them, you'll have them. Okay, so actually taking a step back, the morning science breakouts are going to be focused in the same 7 broad scientific areas as we used yesterday. The cosmology and extragalactic transients are going to swap physical location, but it's the same groupings. We hadn't previously specified areas for the technical breakouts, and so the organizers wanted to propose areas now. So just to kind of get you oriented, the catalog cross-matching, this came up an awful lot. There were 2 other things that you could think of as kind of catalog level things you might want to quantify: the photometric redshifts, including a variety of different aspects, and selection functions and how those will be quantified and described. Then there's access to and reprocessing images. So there were a few groups that mentioned wanting to do some kind of custom stacking or custom sky subtraction or deblending, either for the LSST images or for simulations or whatever. And then time series analysis and image-based object classification problems. So just this last one, this is different from the reprocessing, because reprocessing involves redoing some of the basic image processing steps, whereas the last one, image-based object classification problems, would be like if somebody wants a lot of postage stamps to run a machine learning classifier on them, but they're not actually like reprocessing them. It's more applying a custom algorithm. So we were proposing these 6 broad areas, some of which would have multiple different but related technical problems within them. First of all, I wanted to just pause here and check if there are any comments or suggestions, and people can also put suggestions in the Slack after this. We'll kind of finalize things over lunchtime. But are there any questions or comments at this point? Okay, so now just some procedural things. So we're going to start a science breakout session now. Again, it's the same topic areas, but to prepare us for the afternoon, we have a very different report out template than we had yesterday. It's in the same directory with report out templates. And the goal is to help us connect the science areas we've been working in to the technical challenges. And so just to orient you, the report out is meant to be, instead of for individual science use cases, it's for the entire science area. So like one for cosmology, one for extragalactic transient, and so on. And you can see it's bringing us back to kind of the big picture.
link to the whole folder of use cases, give any like big picture themes that emerged rather than describing specific use cases. And then most importantly, say how members of this team want to participate in the technical breakouts. So like if your science area might benefit from 3 of the, 6 listed technical areas, you could list them here and mention who plans to participate in each of those. That'll give the organizers a sense of, the sizes of the different groups and how to facilitate them, just so that we can make sure we're on track to have a productive afternoon. So that's a different report out, and just to reiterate, that's for the entire, group, not for individual use cases. Based on these inputs from the report out, we'll finalize the technical breakout list during lunchtime and assign locations and facilitators and put an update on that in Slack so that you can refer to it at the start of the technical breakouts, which is after plenary talk that's after lunch. And for the afternoon technical breakouts, we hope that most of you will find an area you want to join. But if you don't feel like you fit into any of those categories, we encourage you to keep working on your draft science use cases and finish cleaning them up and working on them individually or in pairs. And the technical breakouts, will again be in those 6 proposed areas, and they'll follow a similar procedure as the science breakouts in terms of introductions and then splitting up and working on technical use cases. And they have their own report out template. And again, I'm going to put these slides into the Slack after this so you can all refer to them. But I want to check if there are any questions about what we're about to do.
That extragalactic transients and cosmology are switching areas today.
Yeah.
Where were each of them?
So cosmology was in the 5th floor classroom, and extragalactic transients was somewhere in the promenade.
Can I interrupt? The 5th floor classroom is in use, so that room is now switched to the 6th floor conference room.
Oh, okay.
So the 5th floor classroom, I believe, is remaining the same, and then whoever was in that classroom is now in the 6th floor conference.
Okay, maybe could one of the other organizers write that in Slack just so we have that in writing? That would be really helpful. Okay. And I feel like there was one more, Mario?
So maybe just to stress one thing about these outgoing templates. So the idea is, please try to identify any area that your science goal requires to make it work. And we said, try to prioritize them somehow, but even if there are things that are lower priority, still put it there, but also put the people next to each area who are going to go to those breakouts, so that you ensure that if a science area says that, we need these things to get this done, there's at least one person in each one of those breakouts who shows up. So that's kind of what we'd like to achieve.
Yeah, and so the report out template emphasizes the list of names, and also flag if somebody is a remote participant, because if some technical area has a lot of remote participants, then we need to put them in one of the separate rooms rather than in the promenade. Is there another hand? Yeah.
About these technical breakouts, do we have a sense of how the science collaborations, if anything has been happening there, which directly connects here and that can be made use of directly?
Yeah, so so I would say for some of these, there definitely are science collaborations that are working pretty actively. One thing that I'm hoping we'll do is after the report out this morning, we'll have the list of who said they were going to attend which technical breakout, because that's part of the report out. That'll give us an opportunity to see whether some of the groups actively working in a particular area are represented at those breakouts. And if not, we could, try to see what we can do to bring in some more expertise. But that's why we want to get a list of names, so we can make sure that we have a group that can represent some of those efforts.
Okay, so let's get going here. So I'm your moderator for this report back. And then you have to hear me after lunch too. So it's just going to be me all the time now. I'm sorry. I'm going to press slideshow. but do tell me if you need me to refresh for your slide. So let's just get started. We're going to do the same thing we did yesterday. So if you are the speaker, just turn on your mic at your seat and then speak up. Any other logistical things? Don't think so. Cool. So we're starting with Savik.
Hey.
There's some.
Hi. So I am presenting on behalf of the extragalactic variable group, but obviously there was a lot of folks who put in a lot of work on many science cases here. So we have the link to the folder. We fleshed out several really important ones, but we have a photograph and there are many that we didn't really get to. However, there's a lot of big picture comments. We're sending representatives to all of the technical groups. We would like to have extended time baselines, and we think that we can do that with cross-matching and cross-calibration from earlier surveys, which will be very helpful for identifying AGN. And just like a brief note for folks, yesterday we presented on the find all the AGN as soon as possible. This is very valuable for a bunch of reasons, but one thing that's probably broadly of interest is that the better your catalog is, the faster you can do, for example, spatial correlations to find out what types of sources are coming from, what types of LIGO sources, for example, are coming from what types of galaxies. In particular, if there's an AGN contribution, you can do it on just a spatial correlation function. After year one, we're going to want nightly forced photometry on 20 million sources. We will ID them. This is basically, we actually do want to monitor all the AGN, only about, some subset of which will trigger alerts, but very far from all of them. One of the things that we don't understand about AGN is how they vary, we want to figure out what's the best measure of variability characteristics. Is it a PSD? Is it the structure function? Is it something else? We don't know. What is causing it physically? We don't know. AGN monitor on all timescales, including very short and very long. So we want to also be able to turn around with follow-up on those timescales. So we need to monitor them regularly. We need to have follow-up capacity, both for other bands and high cadence photometry, faster than LSST might be providing, and spectroscopy. So that was all very broad and cross-cut many things. Again, for the non-AGN people, it may not be obvious. We don't know how long AGN disks live, to a couple of orders of magnitude. The answer is sort of important if you care about things like feedback. So for everybody who doesn't care about AGN, yes, you do. There's also some use cases that are going to need real-time cutouts, but it is only 10K or less in terms of the volume, but they will need the PSFs. And so there's a question about whether that is going to be provided or how to make that provisioned. And then, we have at least one person going to every technical group and 2 people. Everybody's going to somewhere.
Great. All right. Thanks.
So this is going to be about local universe variables and transients. It was mostly variables, but some areas of transients too. And as you can see from the diagram on the right, we wrote a list of the different workshops and started crossing technical areas, started crossing them out where this group was not particularly interested in, because we assumed that those areas will be handled well and we don't need to do anything specific. So at the bottom, you see that time series is where many of us will be going. Selection function was the other big thing, because as we start getting more and more data, that is where there may be changes that we may see how to do that and improving classification. So the same objects with shorter time series may be classified one way, but as we get more time, more points, that may start changing a little bit. And clearly cross-matching was the other big thing, where we would want to cross-match with not just the recent data from other catalogs, but also longer time scale to see what our objects may have been doing earlier. So that is another area where there will be a lot of emphasis. You can see Gaia, then the southern CSS from Stromlo that exists for a bit. Black Gem is going to be around, so we don't know how much of the data will be public, but again, that's going to be an important thing. And then for many other types, the rest of the electromagnetic range, we'll want to keep an eye on that. And then we did ask ourselves again that whether more of co-hosting will be needed for some of the cataloging services. We know that it is not really part of LSST, but at least some areas where that could be hosted so that one can keep an eye on a large number of variables which have been showing some interesting thing and get something out of that quickly. Feature extraction was another important thing as we get longer and longer time series where we should be going with that. So we'll have a list of features, but what else could be happening there? Automated modeling in terms of, say, what yesterday was presented for macro lensing. We did have a new use case today, which was not fully discussed. That was about techno signatures. So there'll be a little bit of confusion with YSOs, but again, that's something that large changes could be seen in some sources and how one would go about doing that. So again, many different use cases, but all of them revolve around selection function, time series, and cross-matching, and that's something that this group was very interested in.
Great. Andy, there you go.
So this is extragalactic static science. We produced this lovely table, which in all honesty, we stole from local universe static. So thank you for that. We did change the color scheme.
Actually like your color scheme better, but don't tell me.
So here, so we try to identify the three science cases that we have been looking at in detail: low surface brightness features or low surface brightness galaxies, SED or color magnitude diagram fitting, and morphology fitting. Dark here shows you the mapping where we see a strong overlap with the different technical cases. The lighter color is there was some discussion, or maybe it was just a partial usage of image classification or reprocessing of images. The big technical challenges that we talked about were custom processing of postage stamps. And that means having a range of different sizes for the postage stamps, being able to have your own custom sky subtraction, co-addition, and deblending, and running that at scale on, it ranged from a few thousand to tens of millions of sources. Cross-matching came up a lot in terms of questions about the resolution of different data sets and how you do one-to-many or many-to-one matches. The need to be able to support remote tables that aren't necessarily at another archive. If someone has created their own photometric redshift table, for example, how do you cross-match against that efficiently? And then also that cross-matching relates to training data. As we increase the number of data sets that have labels, how do we actually make it so it's easy to both run custom classifications and match the outputs of those classifications, and also do this with the training state data themselves. Today, something new came up in terms of match photometry, and that we're going to have to be able to be matching the PSF, for instance, with if we're looking at mid-infrared data sets and trying to match that to Rubin. And we talked about different packages that do that. And then I've already mentioned classification, the question about how we store outputs from different classifications that are going to be updated every year with each new data release, potentially multiple times each year, particularly in the first 1 to 2 years, as we learn more about the Rubin data sets. And then Cirrus kept coming up as an issue with detection and characterization of low surface brightness. Everybody has a technical topic area that they're going to be going to, and I think we cover almost all of the selection areas or technical areas.
All right, thank you. Oh, I've been on Zoom too much that I thought that I somehow had a Zoom window up on the screen up there. But okay, that's just a photo. Sam.
Can you refresh it?
Yes.
Thank you. So, yeah, I'm going to be representing the extragalactic transients. To go over like the big pictures, main thing for like time series analysis, we want to envision potentially like something like a visualization portal for individual transients, maybe something like the Alerce Explorer page, maybe incorporate something like a Tom toolkit, and involving like other data from other surveys, like getting limits from something that maybe fill the time gap between observations for LSST. We had a lot of questions when it comes with the template strategy, whether it's going to be static or if there's going to be updating of the templates for yearly processing. And that comes into the data reprocessing and access to those images. Another thing that came up with that was potential for co-adding prior to discovery or co-adding post tail fall off for certain light curves to see potential undetected outbursts or precursor images. For catalog cross-messaging, we can envision for like gravitational wave alerts, some complex spatial cross-matching for transients that lie within a contour polygon, something like that. And we know that some progress has been made with a recent paper put out for HealPix Alchemy, which is a Python package that can handle HealPixes really well and do that spatial cross-matching pretty efficiently. Which is like the broad overview of the challenges that we came up with. We have a good representation in all the groups, except for really the selection functions. The only thing we could really think of when it comes to challenges like that is maybe like yearly rates for transients, like supernovae rates and how they compare and how you would select for those analyses.
Great, thank you. Nico.
Okay, so just to recap, we identify 4 main science cases. So low mass stars, mapping the Milky Way in the outer halo. This will be important because there is a rich substructure in the outer halo that LSST will reveal. Then also to identify new dwarf galaxies and stellar streams in the halo and to constrain the stellar IMF. So we find that we need all of these technical things from LSST that are on green, and then we have people attending all of those. And so the big picture comments on technical challenges are catalog level cross-matching with other data sets. At the end, we would like to have like a multidimensional view of the galaxy, so that's needed. But it's also important to know very well the selection functions because we are gonna try to find like the stellar streams, like overdensity areas in the outer halo. So we really need to know and understand the selection functions of both LSST and other catalogs. Also, we need we would like to identify photometric variable stars are needed, such as RL-IRA, low mass stars, rotation of flaring activity. All of these are tracers that are needed for the halo. So we need to understand time series for this identification. And finally, pixel-based techniques are very important to identify distance dwarfs and streams in the outer halo. Yeah.
Cool. Edits make it in.
Yep. So for the solar system, we have a diversity of use cases that depend both on catalogs and images. Roughly, you can think of them as in 3 categories. One is understanding the populations in the solar system, so things like absolute magnitude distributions, size distributions, dynamical parameter distributions, so orbits. Two is the physical characteristics of individual objects. So what is the shape of these objects we're detecting? Are they outgassing? Have they collided and got disrupted? And the third category is going deeper, discovering objects that are farther out in the solar system. Most computationally challenging use cases are those involving additional image analysis. So where we need bulk image downloads to apply detection algorithms that allow us to search for things like Planet 9. And then those use cases that involve catalog and time series post-processing. So given a time series, try to understand what the shape of each object is, and then repeat that for all 5 to 10 million of objects that LSST is likely to discover. So what this group cares about is large-scale image access, so both bulk and cutouts. So in the case of cutouts, it's we know that roughly 1 in 10,000 objects is active, but you don't necessarily know that until you try to look at all the objects and even including co-adding their postage stamps and looking for activity. So we need access to those. We also care about selection functions a lot because all of the population studies depend on knowing very well what the LSST could have detected. So there was a lot of discussion about what is exactly going to be measured and how those data are going to be available. In essence, we need the kind of data that tell us that at this pixel, could LSST have detected a point source and down to what magnitude, and then we can convert that into selection functions for moving object detections. So in terms of the technical breakouts, we care about almost all of them. We tried hard to find a photo Z use case, but failed. But we'll do better next time. And we have a group. We figured out how we're going to disperse between all of these and contribute and listen what others are thinking as well.
I guess how else will you find the interstellar and relativistic asteroids that are coming in?
Extragalactic objects.
Right. And Kate.
Hi everyone, we're the cosmology group, and we thought about our big picture challenges in terms of the technical breakout. So it's kind of all in this table. We stole this table from Extragalactic, who apparently stole it from Local Universe, but we liked the Extragalactic version because they included photo Zs, so thank you. And those are very important for cosmology. So that's a cross-cutting challenge for all of our use cases, and even ones not listed here. So we are sending the majority of our group there. Another one that's important for us is selection functions in terms of the window function of the survey for overlap regions with other surveys, as well as systematics that are going to be really important for shape measurements and other things like that. There are also some uses for cross-matching, perhaps with other spectroscopic or photometric surveys, as well as for definitely supernovae. But we actually were underrepresented in terms of the time series or time domain cases. And so we're not going to send anyone to cross-matching or time series for the supernovae. But if those people in those groups want to keep some cosmology in mind, that would be great. And lastly, there's some use cases not mentioned here that we didn't get to, including strong lensing, which imaging reprocessing is going to be important for. So we're sending Francois there. That's all.
Awesome. Thanks, Kate. Yeah, that's the end of the slide deck. Two announcements that I'll make. I guess maybe we're breaking for lunch early then. All right. Apparently, Fed has an announcement, and then I have two.
I have a question that somebody asked me on Slack. Are the plenaries recordings being posted and where?
Everyone's looking at me. Maybe we should look back there. Yes, I think we are recording the plenaries, and we will post them, I guess, on the Indico page. We'll post links to them as soon as possible. Thank you. Good. Okay, and then two announcements. One is we're going to take a group photo at 4:25 on the roof. So drink something warm before 4:25 and be prepared to stand in the cold for a few minutes or bring a coat. And we'll try to do that quickly and then come back inside. And then at 4:30 we're gonna all come back down here for the technical breakout report outs. And then the other very quick announcement is organizers stay in this room after everyone else goes out to lunch because we're gonna have a little check-in. Yeah.
And following that check-in, on the workshop Slack, there will be an update for everybody about for the technical breakouts, who's facilitating each one, and the locations for each one, because some will need to be in separate rooms to enable Zoom participation. So just stay tuned for an update on Slack via during the lunchtime so that you know where to go in the afternoon.
Good.